Okay, hello everyone. Let's start our lecture. So we have important lecture today. This is last before your homework due date. So I really want you to get familiar with Carnot cycles and how to use it. It's really something important. So let me share my screen and I recall what we did so far. So basically last time we discussed many things, but key point was Carnot cycle, right? So let me recall what we're talking about. What is it? What we're talking about? So basically, remember we discussed that most of actually the process we have in practice are irreversible. We have irreversibilities, which make your process non-idealized. And also we talk about Carnot principles, Carnot corollaries, how we call it, and we prove it, but it's very like, even from naive point of view, you understand it. That, remember, I give you example, all happy families are identical, all unhappy families are unhappy in their own manner. The same story here. If you have two reservoirs, the same reservoirs, what we say? Like here, we say that all reversible cycles operate between these reservoirs would have the maximal efficiency and the same efficiency. It will depend only on their temperatures. True? And that's one principle. It's ideal family. And second principle, that all other cycles operating between these reservoirs will have less efficiency. They will be less effective, as you may see in this picture. Is it understandable? They are unhappy families, they are realistic. So all real cycles are less effective than ideal cycles. And all ideal cycles are identical, provided they are operating between the same reservoirs. Does it make sense? Okay. And what we did next? Then we say, okay, in this slide, let me find one ideal family, which will be etymon for me, which will be saying family I want to look at. And then if I investigate this ideal family, I can tell, am I ideal or not? The same story here. And we came to idea of Carnot cycles. So what is Carnot cycle? It can be back and forward, right? So, and I do request you to remember Carnot cycles. If you wake up overnight, you must remember it. Two isotherms, two adiabats. And I tell it many times, but remember, isothermal and adiabatic are not the same. It's different item. Isothermal means the temperature is constant, while you may have heat transfer. Adiabatic means no heat transfer, while temperature may change. Classical examples, when you cook something on appliance and you have evaporation, you cook at 100 degrees Celsius. Is it isothermal? Yes. Is it adiabatic? Definitely not. You cook, you submit heat to your environment. Okay, opposite examples. I have a piston cylinder assembly. I push piston down. Let's assume my system is insulated, no heat transfer. I push piston down and my environment get preheated. My mixture may preheat it and may even explode. So, is it adiabatic? Yes. Is it isothermal? No. Temperature will change. So, I recall you. So, Carnot cycle consists of two adiabats and two isotherms. Adiabatic, 1, 2, and 3, 4 are adiabatic, 2, 3, and 4, 1 are vice versa, sorry, 1, 2, and 3, 4 are isothermal when heat goes in and goes out, and 2, 3, and 4, 1 are adiabatic when there is no heat transfer. That you must remember and be able to draw this picture and investigate. Because why we talk about it? Because it's the simplest reversible cycle we may have. I cannot invent anything simpler. I can invent something harder, but I cannot invent anything simpler. This is Carnot cycle. Well, since it's reversible, it can go clockwise and counterclockwise, right? And if it goes so when it goes clockwise, what is it? If you see on the picture on the left, QH goes in, QL goes down, so you go clockwise. And this is, what is it? It's power cycle. Work will be positive, work will go out. And definitely you have second reservoir because of second. If you put it counterclockwise, it will mean that heat goes from down to up and this will be refrigeration or heat pump cycle. And here work will be input. Work will be done on the system. You will get it from electricity from outside. Does it make sense for you? And then what we did, we say that let me find the efficiency of Carnot cycle, and this will be maximal possible efficiency for given temperatures, for given reservoirs, correct? And still the assignment I gave you is still on hold. Nobody still submitted, but you can get extra bonus if you really derive equations for Carnot cycle, but not Google and copy, derive and understand. I will clearly see if you derived it or not, because I want you to understand and really well remember. So that is Carnot cycle. But to save time, I will not derive it this time. I will just show you something. I will just show you how it looked like. And remember, or you may say that last time we did it. So that is what we did. So you see downstairs here, the formula that is for Carnot cycle. So formula for Carnot cycle is like this. When temperatures are in Kelvin, remember temperatures here are in Kelvin. It's important to remember this is Kelvin scale. It should be counted from absolute zero. The classical mistake many students do, and many of you are going to do at your third exam, you confuse Celsius and Kelvin. Please don't do it. So that it is. Here you may see efficiency of arbitrary cycle, and here you may see efficiency of Carnot cycle. Okay? And now I can say the following, that if this is my brilliant happy family, then all other families will be identical provided they are brilliant. And all real families like ours, unfortunately, will be worse. True? So that is your strategy, and that is key quantitative point. You know qualitative, what is second law now. This is key quantitative point you preserve now from this how to measure. If you want to check second law, what you do? Consider your device, okay? Calculate your efficiency, how it is. Then calculate Carnot efficiency, how it would be, it was Carnot cycle. And then compare your efficiency to Carnot efficiency, like you may see here. And then you make conclusion. If your efficiency is less than Carnot efficiency, here is reversible one. Then what? Then you say, okay, it's a reversible and possible heat engine. It may exist. That's what we have in practice, right? If they're equal, what you can say from here? You can say, okay, it may be true, it may be not true, but I cannot decline this idea. It potentially may possible. It's theoretically possible that I have reversible heat engine and it works like this. But if you have like this occasionally, what would you say? It's impossible. It's impossible to exceed Carnot efficiency for this given reservoirs. That's what you will do, that's your practice. Do you understand this? Well, and basically what you see here, that your formulas for QL and QH and TL and TH are exactly the same. So just substitute QL by TL and you will get it. Do you understand this? Does it make sense? I hope so. And last time we discussed this example, and I want you to go through the slides again, and we'll do some more examples. So basically, let's see what you have. I recall we have power cycle like this. It's stated that it operates between two reservoirs with given temperature TH and TC or TL, whatever it is. And it is stated that this reservoir is send you 1000, here you get 1000 kilojoule from hot reservoir. Part of it will be converted into work and the rest will be rejected down. Okay, 600 will be rejected down. The question is, please make second law analysis, efficiency analysis, which means identify, is it possible or not? And here you have three options for the temperatures, two for lower temperature, 2, 3, or 400. So what you should do? First of all, and remember we did it last time, but I want you to really get it clear. If you want to pass this course, you must understand this eventually. If not last time, let's understand now. If not now, then tomorrow, but no later than this week. So find your efficiency, how it is. How you'll find it? It will be what is desired or required. It will be, you will find work here, which will be 600, 1000 minus 600 will be 400. So your efficiency will be 40%. And then you will compare your efficiency to what? you will compare your efficiency to Carnot efficiency with respective condition, and then make your conclusion, right? That's what we are doing. Your efficiency will be 40%, right? And then we consider what is maximal theoretical performance, say reversible performance, say Carnot performance. It will be what? It will be if you in this formula substitute T instead of H. So for case A, it will give you 0.6. What is your conclusion here? Do you remember? What is your conclusion? Your conclusion will be okay. Your conclusion will be then maximal efficiency is this one. Okay, it's reversible. Exactly. You're right. It's irreversible and possible. So that might happen. That's what we have in practice. Maybe this is true. And again, please see, it's like semi-quantitative analysis. If my efficiency here will be not 0.4 but 0.59, I will have the same conclusion. Key point, it should be less. Okay. How less, we will talk at the end of this course. Okay, if my in case B, if my low temperature is 300 Kelvin, what I have? I will have exactly the same. So from here, what is my conclusion? That it's theoretically possible, and my system will operate in this condition. Is it true? Well, if you invest money in this project, I would not recommend you. It's maybe not good investment in something hypothetical, but at least it doesn't violate second law. It's potentially it can be possible, right? 150 years ago, if you tell somebody that you invent airplane, nobody will invest money in this, right? People, they would say that people cannot fly, right? But now we have planes. They don't violate second law. So it was theoretically possible to fly, right? But it's theoretically impossible to violate second law. So this case, theoretically possible. But if my TL is 400 Kelvin, then my maximal efficiency will be 20%. And what is my conclusion? My conclusion is, okay, it looks like this efficiency exceeds maximal, which is impossible. It's not impossible because you don't know how it works. It's impossible because it would violate second law. So if somebody give you a proposal with this efficiency, you calculate maximal and say, I don't want to read it. It's impossible according to second law, right? It's impossible according to second law. It does not matter why. It's impossible according to second law. And no reason to investigate. If it was possible, our universe would not exist. We were not born. We were first die and then born. Okay? That it is. So, but please remember one thing, that when you calculate it, you see, when you calculate this point, you should remember exactly the same that once it slows down. I hope you hear me. Something gets slowed down here. So yes, so that's a point. Please, that's your analysis. You calculate your efficiency, or calculate maximal efficiency and compare it. And it does not, you don't need second law should work. If you violate second law, it may not happen. Okay. Now, so and yeah, and what I wanted to say, but when you check second law, you must check first law and make sure that energy conservation works. Because remember, there's quite good illustration here that first, like with this chain on the screen, you first check first law and then you check second law. If first law is violated, occasionally, if energy is not conserved, second law can give you anything. It can give you negative efficiency, larger than 100%. Please don't deal with it. Okay, in your homework, you have a couple of interesting examples. For instance, on my screen now, you see your homework. In your homework, you have example number 3, right? When it's stated that you have power cycle which operates with 2 reservoirs, and there are 4 conditions how QH, QL, and mechanical work can be here. And your task is to investigate how it works and what is possible and what is impossible. Okay, so what you're going to do here? Let me go to my slides and consider this example. Again, I will not finish it until the end, but just give you some hints. So basically what it is. So it's stated your homework problem 3. It is stated that you have heat engine. Again, heat engine is not real engine, it's something that converts heat into work. And it is stated that here your temperature is 700 Kelvin, it's hot reservoir, cold reservoir, sorry, and it's type of here, let me put it will be TL, right? In cold reservoir, you have 300 Kelvin. And basically also that it is, and it's the question is you have 4 cases, A, B, C, and D, and you ask how it works. So is it possible or not? Is it reversible? Is it irreversible? That's what you should address. So let's consider, so what is your task here? First and foremost, let's calculate what is maximal efficiency that you can attain here. And you know that your maximal efficiency will depend on what? On TH and TL. Here is your maximal efficiency. Then what you will do? For each case you have, you will calculate your own efficiency, right? And then you will compare them and make your conclusion, okay? So in your case, what is QH? It's Q in which goes down, right? That's why sometimes Q in goes here, sometimes Q in goes up if you talk about refrigerator. So Q in and Q out goes here. What is QL? It will be here, Q out. So basically that's what it is. What is your maximal efficiency? If you have TL and TH, please calculate what will be here. It will be something like what? It will be 4 over 7, right? It will be like 57%, something like this, right? And then what you will do? You will take case, yeah, you will take case A, case B, and calculate it. So if I have here this case, if I have 700, let's consider case A. I have 700 kilojoules, and mechanical work is 400, and QL is 300. So what will be my efficiency here? Please consider case A. What will be my efficiency? My efficiency will be what? What is desired or what is required? It will be 400 divided by 700, correct? Will it be the same as this one? Exactly. So what is your conclusion for case A? Exactly, it will be reversible. I don't write it down, I want you to solve it yourself, but you realize it is case A when TL over TH corresponds to QL over QH, they cancel, right? So it will be, so it's theoretically possible. Let's talk about case B. What about case B? What do you see in case B? What will be your efficiency in case B? If you have QL is 400, this is 500, this is 700. What will be efficiency in case B? So what is your conclusion then? Right? It will be impossible. Why it will be impossible? Because your efficiency exceeds potentially maximum. Looks trivial, but not so trivial. Okay, let's consider case 3. See, what will be in case 3? Again, yeah, very good point people ask. So what case 3? If I write Vmax over QH, what I will have? I will have 3 over 7. But if I write last formula, 1 minus QL over QH, I will have what? I will have 1 over 7. So what does it mean? So don't you think this formula and this formula give me something different? Why? Exactly. So do you think I did some typo here? No, I did not. That's what I want you to catch. Check first law. Check this and check this. Okay? Is energy conserved in case C? No. So what does it mean if energy is not conserved? It means that no reason to talk about second law. Second law gives you anything. If energy is not conserved, I can get, it's impossible. And no reason to talk about second law, correct? So in that case, remember again, Remember what I just showed you. First check first law, then second law. If first law does not work, no reason to deal with second law. Okay, right? And here we are here, right? So basically, and if you consider case D, well, first law works here well. So now you may see that what is your efficiency here? Your efficiency will be 600 over 7. So what would it mean? Then again, it's impossible. So do you understand what we are talking about? Will you be able to solve all these problems? That's what you must do. That you check your efficiency, check maximal efficiency and compare. And then what you will do, look here and compare, right? Look here and compare. Do you understand this? What you must remember here? You must remember that temperature is in Kelvin scale. If you write in Celsius scales, it will be something ridiculous. So like you see on the screen now, that's what we have. We have that heat, let's see what we have. We have heat engine operating between 1000 Kelvin and 300 Kelvin. And we say that its efficiency is 70%. What does it mean? Well, we check it here, right? So basically, if it's 70%, it will mean that it's reversible, right? If it's efficiency like say 45%, it will mean that it's okay, it may happen that it's irreversible. If you find that its efficiency is 80%, believe me, you did something wrong, it's impossible. So what you see on the screen, it's really bottom line of chapter 6, what you should, at least what you should remember about heat engine, about power cycles. Well, also sometimes you have Carnot cycles, and then I tell you, please read the text body very well. For instance, you have good example 6.5 in your homework, in your textbook, and very good, and it's very similar to problem number 4 in your homework. So let's deal with it. That I want you to show. Here it is. So basically, here it is. So what we should do here? Basically, this is from your basically. This is an example from your textbook. Let me just go like this, okay? So what is stated here? It's, for example, 6.5. So what you have here? It's stated that you have, again, power cycle, which operates between two reservoirs. Hot reservoir has 652 Celsius, heat Celsius, pay attention. And cold reservoir has 30 Celsius, pay attention, it's Celsius. So what you will need to do, you convert it into Kelvin. And it's stated here that QH, that heat which goes from hot body, from hot reservoir, is 500 kilojoules, okay? That's what you have here. And the question is, okay, please find efficiency of this engine. Key point, find thermal efficiency as well as heat rejected downstairs, that is QL. How to find efficiency? So what are you going to do? What you should know here? Find efficiency. You write this formula. That is your formula for thermal efficiency, right? Do you remember this? In this equation, please look at this equation. People ask about the heat pump and no, is heat engine is the same as a heat pump? Not. It's fully opposite. It's fully vice versa. I recall that heat engine operates in a power cycle. I recall it's not engine in practice. Heat engine converts heat into work. As you see on the screen, you have hot body, cold body, two reservoirs. Heat goes here from top to the bottom. You convert heat into work, okay? And part of this heat will be rejected down. That is heat engine. Heat pump and refrigeration cycle are fully opposite. It operates in different manner. And heat will go from here up and some work will be added. Okay, we will talk about this in about 10-15 minutes. Okay, we will talk about it. Now, how it may happen that first law fails? Well, it cannot happen. That's why I give you this example. It cannot happen. That's why when you come to this statement, it means that your system does not work. Moreover, second law also cannot fail. It cannot happen. So don't think that second law like it's easy to violate as compared to first law. It may definitely, it may not happen. That's what I tell you. If energy is not conserved, your system is wrong. It does not exist. It cannot happen, of course. Okay? That it is. And case C, of course, is impossible. It's impossible to violate second law. Come back here. So how to solve this problem? How to solve this example? How you find efficiency? I write my efficiency is work out over Q int, and this is my formula. So how many equations I have here? I have two equations, right? Because two sign equal, so it's two equations. Okay. For two equations, I should have two unknowns. How many unknowns I have? How many variables I have? I have four variables, 1, 2, 3, 4, right? QL, QH, you understand here that QL is Q out, QH is Q in, right? So you have four variables, theta, work, QL, QH. I have four values. What do I know here? I know QH, okay? I know QH. So, can I find everything else? I believe not. So this is my one equation. This is my second equation. I have two equations and I have only one known value. It looks like I cannot solve it. I need something else, right? But now you know what to do. What you do. It's stated, if you read the text body, it's Carnot heat engine. So read the text body. Something is stated. Carnot heat engine, maximal heat engine, internally reversible heat engine operating at a reversible manner. Read it. If it's stated, or it's stated, please find maximal efficiency. If it's like this, you know, okay, I operate at Carnot conditions. I have a happy family, and all happy families are ideal. So I will compare it with Carnot efficiency. So now I'm lucky. I know that I have one more equations. What do I know here? I know that my coefficient of efficiency coefficient is equal to maximal. Okay, so now I have this equation, and with this equation I will know everything. So my maximal efficiency is equal to what? It is this formula. Can I calculate it from here? How can I calculate? Yeah. So what I will do here? I will write like this. I will calculate. And what is my TL? What is my TH? First of all, will I write it like this? Will I write it like 30 over 652? Will I write like this?
Kelvin.
Exactly. That's what I try to catch you. Believe me, I'm not wrong here. I want to catch you.
You
Excellent.
almost had me.
Because what I did here, it's exactly what many of you are going to do in your exam. Plus 273. Plus, or 0.15, but you can write 273 for simplicity. 273, right? That it is. That it is. And when you calculate it, you will come to what? You can look at your textbook, it will be like 67%, something like this. It will be 67.2%. Okay? So does it make sense? Now I know this value. So if I know this value, will I be able to calculate my value here? My QL? Yes, this is what I have, correct? So do I know QH? Will I be able to calculate QL from here? Yes. And you will get that QL will be what? QL will be something like 142, 164, I'm sorry, 164 kilojoules. Do you understand this? Do you understand why? Yes, that is what most important. Because Carnot efficiency gave you one more equation. Now you know that your thermal efficiency is maximal efficiency, and you calculate. Does it make sense? Moreover, you can actually get from here very simple that this value is equal to, it will be even simpler for you. You can calculate this value, it will be like TL over TH. And from this equation, you can calculate itself. Does it make sense for you? Do you understand this? I hope so. In your homework, you have very simple, very similar examples, exactly almost the same. The only point is it's like vice versa. So in your homework, it will be the following. In your homework, it will be, it's problem number, homework 6, problem number 4. So what you have? Let's take a look. Here you have that you have heat engine receives heat from a source of 800 Celsius and rejects heat to a sink at 40 degrees Celsius. And it's stated that heat is rejected to a sink with a rate of 80 kilojoule per second. In fact, it will be almost the same, but it will be not Q, it will be heat rate. It will be Q dot value, right? So what we will have here? So exactly similar problem here. So what I have? Like I did here. The only difference here I will have 800 Celsius, right? Here I will have 40 Celsius. And the only difference will be that QH, it will be, okay, sorry, it will be not QH, it will be QL, which is 80 kilojoule actually per second. It will be per unit time. So it will be not QL, it will be actually QL dot if you calculate it, right? So, and it will be here, correct? Exactly the same question in your homework. It asks, please determine the maximal, and what is stated here? Please determine the maximal efficiency of this heat engine and justify if it's possible for this engine to produce 100 kilowatts. So what are you going to do? Exactly, it's very similar to what we had here. So write down your equations. So that is your efficiency. And basically, when you write like this, what you know here? Unlike example from the textbook, you know QL here, okay? You know QL, but you don't know QH. You need something else. And what something else will have? It stated that you look for maximal efficiency. If you look for maximal efficiency, it means that you deal with what? With Carnot cycle, exactly? Yes. Yes, and exactly a very good point. Convert Kelvin to Kelvin first, right? So you will find your efficiency based on this. Will you substitute and calculate? Right? So you will know your efficiency. And based on this, will you be able to calculate QL, you know, QH, and work output? Will you get work output from here? Do you understand how to do it? Work out will go from this equation, right? You already know this value. Already know this value. You will find this value from here. You will find work out. And then you will see, okay, if it's larger than 100 kilowatt, then it's okay, it's possible. Otherwise, it will be impossible. Do you understand this? Again, this is your homework. I don't want to solve this problem in full. I want you to come home or just when you have free time and solve it yourself from scratch. It's important that you understand. And what I want you to realize that for Carnot cycles, what we have this one is equal to this. That is really easy to use. And formulas for Q and formulas for H really practically coincide. Why I say this? So because that's actually how Kelvin scale originally was implemented. Look here, please. Let me see. I'm sorry for the, yeah. Yes, basically how Kelvin scale appeared at the very beginning. So please, okay, you know, now we know what is absolute zero. There is absolute zero because this is a value at which no motion or no chaotic motion of molecules. And when they move, your temperature is high, right? But when Lord Kelvin developed this, when he did not know this, right? So how he arrived to the idea of absolute zero? He says the following. He says that it should be reference frame in which temperature should be proportional to heat transfer for a reversible cycle. Imagine he invented like this. And then he looked for this temperature. Now we know that it's minus 273 degrees Celsius or minus 460 degrees Fahrenheit. He did not know this. That's how he defines this. So that's how he defined Kelvin scale based on this condition. Does it make sense for you? That's how he defined it. And that's how he came that for Carnot cycle, this equation should work. For this will be definition of temperature for Carnot cycle. That's how he arrived to this point, and that's how he arrived to minus 273 degrees. We know this from tables from childhood, so we don't understand this. He did not know. Is it absolute zero minus 1,000 or minus million? He got it from this ratio. He says that absolute zero it's the temperature at which all cycles should be reversible. When you have cold reservoirs at absolute zero. Does it make sense for you? Is it understandable? Okay, very good. Now, that's how he arrived to this. And now that was for power cycles. But remember, we talk also about refrigeration cycle. They work in a similar manner because now we know that energy has a quality. If you have higher temperature, this energy has higher quality. Why? Because you cannot convert heat entirely into work, correct? Please realize it. So, now, remember what is refrigeration cycle? And it was a question on the screen, now I recall it. Refrigeration cycle, heat pump cycle, does vice versa. It does not convert heat into work. It transfers heat from cold to hot source. That's what it does. And you know now that you need to deposit some work to make it feasible, right? It's Clausius statement on the second law, that your fridge does not work for free. Now, remember when I plotted Carnot cycle for you, I tell you that it can go straight in this way, clockwise and counterclockwise, right? Do you believe me that I can do the same derivations for fridge and for heat pump? Do you believe me? Do you believe me that I can say the same Carnot principles for heat pump and refrigeration cycle? That I will say that as soon as I have the thermal efficiency of reversible power cycle is less than thermal efficiency of reversible, I can say, and coefficient of performance of reversible is less than irreversible. Can I say in the same manner that coefficient of performance of irreversible refrigeration cycle is always less than coefficient of performance of reversible refrigeration cycle? Do you believe me with this? And do you believe me in the same for heat pump? And do you believe me that all reversible heat pump operating between the same reservoirs will have the same efficiency and it will be maximal efficiency? Right? And all other heat pumps and fridge will work at low efficiency. Correct? So it will be, and do you agree and do you understand that formulas will be like very symmetric? That if this is maximal efficiency for my heat engine, then this will be maximal efficiency for my refrigeration cycle. And this will be maximal efficiency for heat pump. And formulas are exactly like we had for power cycle, heat refrigeration or heat pump. Instead of Q, I write here T. And you understand why? Because remember how Kelvin defined it. At absolute zero, all cycles are reversible. And its scale was defined when Q is proportional to T. Do you understand this? So that is the main formula. So do you understand now that how you will check if your heat pump or our fridge is feasible or not? Again, find your coefficient of performance. Find maximal coefficient of performance. Compare and make a conclusion. Is it reversible? Is it irreversible? Or is it impossible? If it's reversible, it's theoretically possible. If it's irreversible, it's possible really, and your efficiency is less than maximum. Do you understand this? Is it trivial? And that's why, remember, last weekend I sent you the summary power slides. In this list that you have, really there is a summary of everything you need in this chapter. So this is a formula for thermal efficiency and for maximal thermal efficiency. You see it on my screen? correct? I believe you see it. Here is coefficient of performance. Here is maximal coefficient of performance. Here is for heat pump. Here is for refrigeration cycle. And then how you can make your analysis? You look here. Find your efficiency and compare. If your efficiency, if your coefficiency or coefficient of performance does not matter, if eta or beta or gamma is less than maximal, it's irreversible and possible in practical reality. If your theta or beta or gamma are equal to maximal ones, it's reversible and it's possible only theoretically. I would not believe in it, but it may happen. You cannot decline. If you cannot make it, it does not mean it does not exist. It may happen. While if your eta, beta, or gamma larger than maximal, it's impossible because this would violate second law. It's not because you don't know how to do it. It was because our universe exists. You would violate second law. Remember Carnot cycle. This is a list that you really need to know. And exactly the same point for refrigeration and heat pump. Read the text body. Like I solved just problem in the textbook for heat engine. And the same for heat pump and refrigeration cycle. If it's stated that find maximal coefficient of performance of heat pump, or you have Carnot heat pump, or you have heat pump operating in reversible manner, it means it's Carnot. It means you can say that what you see here is equal to that one. Do you understand this? Do you understand this? I believe so. That's most important, and that you need to understand. Okay. Yes, and when you talk about refrigeration cycle, when we talk about cycles, a very good question about science, and we will talk about this now. This work that you see here is absolute value of work. Of course, it's negative from the viewpoint of refrigeration on heat pump cycle, but we talk about absolute values here. Now, so that it is, and I want you to show something and in fact, you have a very good example in your textbook. It's example 6.6, and I give you and please go through it. We don't have time now to do it, but I want you to give you some hint about your homework. So please read, look at my screen and see what you have in your homework. Basically that it is, you have that what you see in your homework. So basically it's stated, you have refrigeration cycle here, which operates with Freon in this cycle, and it is stated, please determine the rate of heat rejected from the condenser, and please determine the rate of heat absorption and coefficient of performance. So key point is the following. Now, I believe I tell you, you should be able to consider this device at zoom view and in general. So look at this picture. So what is refrigeration cycle, right? You have operator, condenser, compressor, expansion valve, and you go counterclockwise here, right? So each of these devices is what? It's a subject of chapter 5. In chapter 5, you consider all of them. This is state 1, this is state 2, and so on. And if you look here, yes, this work input will be negative because it works on your compressor. From the point of view of your compressor, it will be negative. But when you write down equation for coefficient of performance, you take absolute value. So let's look at this problem. What is stated here? And let me clean it. It's stated that Freon enters condenser at 800 kilopascals and enters at exit at x equal to 0, which means that it will condense. So basically what happened here? So you consider two problems. One problem, consider condenser only. So here it is. So you zoom, you actually you zoom your problem, right? What does it mean that you zoom your problem? You do like this. You consider like this, right? Okay, you consider like this. So this is your condenser. Where is your state 1 here? And forget about everything else. So here is your problem. Here is your state 1, okay? Inlet. Here is your state 1. It's your inlet, okay? So will you be able to identify state 1? Here you have Freon at 800 kilopascals and 35 degrees Celsius. Will you be able to identify it? Yes? Again, like usually, you are in chapter 3 now. That's why chapter 3 is backbone of the course. If you forgot chapter 3, no reason to talk about second law. Assume this is saturated mixture and blah, blah, blah. Check if it's true or not. You will see most likely it will be superheated vapor, and you will find whatever you need. You will find all values you need. You will find H1, you may find U1, whatever it is, V1 if you want, whatever is defined. Here you will need H1, right? Now, this is state 2, okay? This is state 2. Do you know state 2 here? Again, you have 800 kilopascals, the same is here, and you have quality of 0. So it will be what? It will be saturated mixture, right? It will be saturated liquid. So your H2 will be what? It will be HF at this given pressure, correct? Will you be able to find it? So you know H1 and H2. So what is heat transfer here between state 1? You will have that your Q here, it will be what? What will you write? You will write down your big first law equation. dE over dt is equal to Q minus W plus CV, blah, 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 and so on. In your case, it will be this equation. Q dot is equal to M dot H1 minus H2, correct? Why I write H1? Because H1 will be larger than H2. Heat goes out, right? So that's, you solve it, okay? And that is your QH, correct? And now what you do next? Now you zoom your problem. What does it mean you zoom your problem? Now you will consider this problem from big screen. You will consider, you go far away, far away, far away, far away, far away. I'm too far. Okay, far away. But key point that now you will consider this like one box. You have TH. You have, right? You have TL, right? You have work input. And you have QH, which goes here, and QL, which goes here. And you have coefficient of performance, which will be what? Which will be QH divided by work input. And it will be QH divided by QH minus QL. I'm sorry, I did mistake here. It's not QH, it's QL, because you talk about refrigeration cycle. I also do mistakes. It's okay. Key point that you don't do mistakes, okay? Like this. But you know QH from what? From first consideration when you saw it from condenser. Now you consider it from big screen and consider it entirely and solve it. Does it make sense for you? Okay. Any question at this point? So I will stop it because just 50 minutes. I will stop at this point. But I want you to realize what we are doing, and again remember the screen. So if you see from Zoom screen, here is your refrigeration. So now you know you got QH from condenser. Now you consider it from big screen. Zoom in. In your homework, you also have problem number 6 about heat pump. It's quite similar, but you should realize the following. They ask you how it would work. There are two questions. First, you consider real heat pump. Then it's stated how it would work if it was Carnot heat pump. You know what to do then. Carnot heat pump, you replace Q by T and solve. But then there will be another question in problem number 6. What if you have electric resistance? How it would work? Key point is the following. Heat pump, you're lucky. You submit work input, but QH goes in. So coefficient of performance, which is gamma, it will be QH divided by work input, right? You're lucky. In general case, you're lucky because you put in work input and QH goes to environment. If you use resistor heater, then work input will be, then it will be work input which should go out. So your system will work coefficient of performance times worth. Okay, by the way, it was lecture number 30 today, 30. We are approaching the end of the semesters. By the way, fill out a student evaluations of instructors. They are open and I appreciate it. And now, again, we will have help sessions today and tomorrow from 5 to 7. Please join us. It's really very helpful, especially if you face troubles. It's very helpful. I cannot solve all examples in the class. So your homework is due Wednesday, and also we will start next chapter on Wednesday because your exam is approaching. Well, so I will extend homework to due end of Wednesday, but the earlier you submit, the better. Okay? Okay, because we may do some examples still in the class, but that is most important. Okay, thank you then, and see you on Wednesday. And I will now I will stop recording.